Hello everybody, this is Lorenzo Perella for Physics 116 Clark Wellman's class. Now I haven't done a lab in a while, but we're going to go right back to it and get into lab 6, which talks about reflection, refraction, and dispersion. On this case, we'll be using Snell's Law in order to figure out the mystery index of a mysterious substance. To do this, we'll be using a simulation from Colorado University that talks about bending light. In this one, we have is a light ray that we can change the angle to in order to find the total internal refraction. And it means that N1, which is mystery A, has to be greater than 1. Otherwise, when you make the internal refraction, this would not be able to happen. An example of this is if you have water into air. See, water is greater than air, so you don't see the total refraction on the other instance. However, if you change it back to mystery A, we do see a total internal refraction. Now, we're supposed to do this for all of the wavelengths between 400 nanometers and 700 nanometers, which is the visible spectrum of light. And to do this, as you can see from here, we have a P normal length, and then Q is the refracted angle. To get the total internal refraction, we set N1 times sine of theta 1 equals sine 2 n sine theta 2 n2. Now in our calculations, an example of this is right here, where we have the first angle is 24.5 degrees and the second theta is 88.88 degrees at 700 nanometers, which would be the color red. To get the coloration for this, what we do is set n1 times sine of 23.9. Oh, sorry, this one's for 400 nanometers. My bad. This one is the one we're doing right now. So n1 times sine of 24.5 degrees equals sine of 88.88 degrees times 1, because 1 is the refractive index of air, and anything times 1 is just here. So then we get n1 is equal to sine of 88 divided by sine of 24.5, which is roughly 2.41. We do this for every 20 increment of wavelength, and we graph that. This graph I made on paper and pen to the best of my ability to a relative spectra. And as you can see, we originally start at 2.46 at 400 nanometers and work all the way down to 2.41. When we graph this with y equals mx plus b, we know that b is the y-intercept, 2.46, and that the change in m is 2.46 minus 2.41 divided by 300, that being nanometers. And the result is 1.667 e minus 4, which is the result of nanometer, which is the refractive index change per nanometer. We can rewrite it as y equals negative 1.66 e minus 4 x plus 2.46. Now for every nanometer, the refractive index decreases by this level. Now, finally, the average would be the two extremes would be 2.41 plus 2.46 divided by 2, which gives us an average in total reflection index of 2.435. And this will and so long as the first n is greater than the second n, the total internal refraction stands. Thank you. This has been Lorenzo Perella for Physics 116 Clark Wellman's class. Have a wonderful day.